Coming up on Dr. Kiki's Science Hour, we're going to be talking about radio telescopes with Joseph Lazio from JPL. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with Dr. Kiki Sanford, recorded on Thursday, May 26, 2011. Radio Flyer. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies streamed to your PC, Mac, or TV instantly. Plus, get DVDs by mail in about one business day. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to another episode of Dr. Kiki's Science Hour. I'm Dr. Kiki Sanford, and I hope you're here ready to dig into the science because, as usual, it's 1 hour, one topic, one expert. And today, our topic is radio telescopes. We're going to be talking all about how we collect radio signals using these telescope arrays to collect signals from space. And our guest today is Dr. Joseph Lazio. He's a radio astronomer who currently works with JPL and is also deputy director of the Lunar University Network for Astrophysics Research. He received his PhD in astronomy from Cornell University and has a history of science writing. You might have seen his work in Scientific American. He has also worked or works as well on the Square Kilometer Array and is currently working on the Long Wavelength Array, both of which are radio telescopes. So hopefully, Joseph, you know a little bit of a thing or two about radio telescopes. Thanks for joining me today.
You're welcome. I'm pleased to be here.
Yeah. So what got you interested in astronomy and led you on the path of becoming a radio astronomer?
Ooh, I can't fully answer that question because I remember being interested in science for as long as I can remember really any interest. I certainly went through the phase of enjoying, thinking about or being fascinated by dinosaurs. Somewhere along the line, astronomy piqued my interest, and I never lost that. I'm very much the kid who, when you would have asked me what I wanted to do, I don't know, when I was in elementary school or something, I wanted to grow up and be at least a scientist and probably an astronomer. So I'm the kid who got to grow up and do what he always wanted to do. The way I got interested in radio astronomy specifically is when I was young in the 1970s, and I would bike down to my public library and devour all the books that I could on astronomy. One of the hot topics in the 70s was an emerging technique in which we can take radio telescopes, or at the time it was emerging and now it's a very routine process. We can take radio telescopes that are spread out, and by combining them in the appropriate manner, one can effectively synthesize a telescope that's as large as the separation between the individual radio telescopes. And at the time in the 1970s, this was being done, or what was being pioneered was actually the ability to tie together radio telescopes from all over the planet, effectively synthesizing a radio telescope comparable in size to the diameter of this planet. That just sounded really fascinating. It then means that one can peer into the very cores, the very hearts of galaxies. The other nice thing about radio astronomy is that we can observe, like right now, when the sun is up. So in principle, that means one doesn't have to stay up all night in order to get one's data or to do a radio telescope observation. And certainly that notion of being able to do radio astronomy or do astronomy without having to worry about the sky being dark and losing lots of sleep had an attractive aspect to it as well.
I guess anyone who, if you're getting into radio astronomy, you'd better be ready to stay up all night because you're going to be collecting, can be collecting data at any hour of the day, right?
Yes, but I take the other spin on that. That means we don't necessarily have to stay up all night. We can possibly do it during the day. And Whereas opposed to, say optical astronomers, the only way that you can collect your data, well, actually that's not true now with the Hubble Space Telescope, say, but certainly it used to be the case that in order to do optical astronomy, you really had to stay up all night, and that isn't necessarily the case for radio astronomy.
How much has radio astronomy developed over the last 40 years? So since the 1970s, and that amazing idea of being able to have a radio telescope the size of the planet, basically by connecting all of the radio detectors around the planet together. How far have we come since that idea?
We've made incredible strides. Of course, in terms of making an even larger telescope, there's been one spacecraft mission launched by the Japanese, in which they put a radio telescope in space and then tied together with the radio telescopes on the ground. They were able to synthesize a radio telescope that was actually larger than the planet itself, or larger than the Earth itself. But we've done an enormous number of things, or the radio astronomy community has done an enormous number of things in terms of probing a vast range of phenomena, looking at things that one can't see with optical telescopes. And indeed, that's one of the reasons that we do the various kinds of astronomy, not just radio astronomy and optical astronomy, but X-ray, gamma ray, infrared, is that we obtain a much more diverse, much deeper understanding of the universe by looking at all these wave bands, of which radio is a very important one. So it's been everything from studying planets in our own solar system to looking at nearby stars and trying to understand how their magnetic fields, or how they act, and how that might have influences, or how it might help us understand our own star, the sun. There have been studies of very compact, very dense remnants, essentially the ashes from very massive stars, and they probe fundamental physics at exquisite detail, just incredible detail, to looking at some of the most distant galaxies. And in fact, one of the areas in which radio astronomers are trying to probe today is actually seeing back to a time before there were any stars. And then also just trying to expand some of the early work that I was, for instance, when I was a boy and reading about it, it was at a very narrow wavelength, or a very specific, if you like, a specific color, or a small range of colors, radio colors, if you will. And we've now expanded that to cover a whole range of radio wavelengths, or radio colors, from wavelengths that are larger than the room in which I'm sitting, to things that are wavelengths that are really that small. And again, it's driven by a diverse range of science goals to probe the various phenomena and probe the objects that are generating those kind of radio emissions.
So let's get down to some basics of radio astronomy. You've talked a little bit about how you look at different wavelengths, and
yes,
that the different wavelengths allow you to delve into different scientific questions. How does that work?
This is actually a very important thing. In fact, if people listening to this take away nothing else from this conversation of ours, I hope they take away the notion that radio is actually no different than the optical light that we use, that our eyes see. Of course, everybody's familiar with a rainbow, red, orange, yellow, green, blue, violet. What you are probably also aware is that there are colors that our eyes can't see. And anybody, for instance, who's gotten a sunburn is quite familiar with ultraviolet light. Well, what is ultraviolet light? It's light that's more violet than violet. And by the same token, there's infrared light, which is essentially colors of light that are more red than red. And then you can extend that. If you go beyond violet and beyond ultraviolet, you hit X-ray and then gamma rays. And in the other direction, if you go beyond red, so you go to colors of red, or colors of light that are more red than red, you go infrared, or you get to the infrared part of the band. And then beyond that, you get into the radio band. The radio band is sometimes broken down into, for instance, microwave and radio. But the general notion is all of this entire spectrum, all these different kinds of waves or light, are really just the same thing. They're electromagnetic radiation, and what differentiates them is a wavelength. They, if you can see me actually gesticulating here, if you imagine actually water waves, that's a very good example. Water waves with different wavelengths are still water waves, and the difference between X-ray, ultraviolet, optical, infrared, and radio wavelengths, it's really just the radio, it's just the wavelengths, or if you like, the color of the light. But they're all essentially the same phenomenon. They are, however, generated by different processes, and therefore, again, the analogy I often like to make is, suppose you were to look out the window and the only color you could see was red. Well, that would give you a very limited view of what's out the window or of the universe in general. And that's why we want to look at all these different wavelengths and radio probes certain things that you can't see any other way.
For how you're looking at them, what kind of instruments do you need to be able to detect different wavelengths? I was really struck by your idea of water, and I'm thinking about, waves in the ocean. And could you actually just, if you were just looking at the wavelength of the waves on the ocean, you could probably extrapolate an actual sound from that as well?
Yeah, so I think the way I would say it is more you would extrapolate to some understanding of the process that's generating that size of wavelength. Very short waves must be generated by something perhaps slightly different than much larger waves, or perhaps because it's in everybody's mind, or it's been recently in everybody's mind. If you imagine undersea earthquake, that will generate, because of the way that the seafloor would drop, or the shaking that would occur under the water, that would generate wavelengths of a certain kind that would be different than, say, wind blowing over the surface of the water. And it's a sort of a similar notion of wavelengths. Different kinds of wavelengths, different kinds of electromagnetic wavelengths or light wavelengths are generated by different processes. If we can get back actually to return to your earlier question of how do you actually collect this radiation, most people are actually familiar with this. If you have a dish network, you essentially have a small radio telescope sitting on top of your house. In this particular case, it's collecting the radio signals from a satellite, and it can be relatively small because the satellite is relatively close to us and has a fair amount of power. If you look, however, at radio telescopes that astronomers use, they tend to be very big. A typical or a common diameter of telescopes that I use is 25 meters, so that's something like 80 feet across. And certainly, for instance, the United States operates a couple of the world's largest telescopes. One is the Green Bank telescope in West Virginia, which is 100 meters across. And then there's also the Arecibo telescope in Puerto Rico, which is 300 meters across, or 1,000 feet. And those sizes are dictated by the fact that radio wavelengths are just larger than, say, optical wavelengths.
So you have to have a bigger dish to be able to get bigger wavelengths, to collect bigger wavelengths? Okay.
Exactly correct, yes.
And do you have to, when you're thinking about where things are coming from in space, you mentioned earlier that you could be looking at things relatively local to us, events that are occurring in our local environment, or say in the sun, or we could be looking at stuff from the beginning of the universe, so way back in history. How do you have to understand, I mean, is there attenuation of the signal based on the distance that it has to travel? Is there a change in the signal?
There is certainly attenuation in the sense of more distant objects tend to be fainter. There is, I don't have an immediate analogy from everyday life other than, for instance, if you imagine taking a flashlight, or if you imagine, I mean, it's the same principles applies to our everyday life. If you imagine taking a light and moving it farther away, it will get dimmer. And that's just the same. If you saw me smiling during part of what you were saying, one of the actual interesting aspects about radio astronomy, and again, to emphasize why we want to look at all these different wavelengths, if you've ever for instance, been in a fog bank, you know that at optical wavelengths, it sometimes can be very difficult to see because of obscuration or attenuation caused by stuff that is, say, in the medium around you, in the air around you.
Right.
But by the same token, if you've ever been in a fog bank, say in a car, it may be very difficult to see. Your headlights don't penetrate very far, but the radio signals to your radio, your FM radio, still come in quite fine, and that's because the fog particles aren't the radio waves aren't affected by the fog particles, whereas the visible light that we see is. And in fact, this principle not only applies, say, to driving through a fog bank, but it also applies in the galaxy. That if you want to peer into the very dusty regions, the clouds where stars are forming, you can't see in there with visible light because it's too obscured. The particles are not water vapor as they are in a fog bank, but they're actually little dust particles. Whereas at infrared and radio wavelengths, we see right in and can effectively watch stars form. And in fact, one of the goals of both some current generation telescopes, and then you mentioned the square kilometer array in your introduction, next generation telescopes is actually be able to peer in and watch these stars as they form, and potentially even watch the areas where planets might be forming, and see the processes that take place. And we can do that because we're not affected by the dust that is surrounding stars as they form.
Right. The wavelengths that as you mentioned, the wavelengths are much longer, so there's not as much interference.
Yeah, I mean, the wavelengths, is, if you can see me actually holding up my fingers, if you imagine looking at wavelengths that are this big, these wavelengths are not affected by dust particles that are microscopic. We see right through them. Right. Whereas a microscopic dust particle, or a bunch of microscopic dust particles, is a real problem for optical wavelengths such as what we see.
All right, so how do you discern what's going on when a star is being born based on the signals, the radio signals that you get? So you mentioned earlier, trying to figure out how the waves on the ocean, the big waves, what's causing larger wavelength waves to form versus smaller ones. How do you figure out what's going on in a star?
There are two things that we would do, or there are two broad ways to approach this problem. One is that all elements, all molecules put out very specific wavelengths of light. And in fact, again, everybody is familiar with this concept in the sense of, if you've ever seen a neon light gets its name specifically because it is light that is being, the color of light that is being generated is generated from a neon atom or a set of neon atoms. And they produce light at a very specific color. The same thing actually with a laser pointer or a laser light. That's a very specific color, and that's coming from the exact atoms or the kinds of atoms that are being used in that laser. That principle applies in general, that all kinds of different atoms and molecules produce specific wavelengths, and if you can detect those specific wavelengths, it tells you something about, immediately tells you something about the composition of the object at which you're looking. So for instance, if you look at a cloud of gas and you see the specific wavelengths that are attributed to water, you know immediately, aha, there's a certain amount of water in this cloud from which this star is forming. That's one way. The other way is you actually go and effectively take pictures or make images of the regions. And that is one of the areas in which this process or this technique of tying together telescopes becomes important. As you tie together these telescopes, you effectively improve how fine of a detail you can see within, say, a cloud or within a region. Thus, what we do is we, say, tie together these telescopes and can peer in and actually see, aha, here's a little clump within the larger cloud. And this little clump is an area where the gas is perhaps a little bit denser and a little bit hotter. And so that's clearly a clump where it looks like stuff is starting to contract and form into a star. And if you then do that in several other places, here you make an image of this cloud and you see, aha, here's this little clump and here's this little clump, and perhaps they have slightly different sizes or slightly different temperatures. You end up deciding, aha, this is an area, say, where stars are forming.
All right. For looking at as you mentioned, the getting finer detail with tying telescopes together. That's what you're doing currently with the square kilometer array and the large wavelength array, correct?
In a sense, the square kilometer array is still under development, but there are certainly a number of other telescopes. For instance, in the United States, there's the expanded Very Large Array in New Mexico. Certainly, as you say, the Long Wavelength Array does this. There's also a telescope called the Very Long Baseline Array that it really is that original notion I described of there are 10 telescopes spread across the United States. And then there's a similar telescope in the Netherlands, a similar telescope in Australia and India that operate on this same principle of you take some number of telescopes, anywhere from, say, 10 to 30, and by combining the signals in the appropriate fashion, you effectively synthesize a much larger telescope than any one of the individual ones.
What is the purpose of the square kilometer array and the long wavelength array? We've got these different telescopes that are being put together. You know, they take up a square kilometer or, you know, other sizes and can detect different wavelengths. What are their specific purposes?
The two you described are somewhat disjoint. Let's start with the long wavelength array. The LWA is very much intended, or the original goal was certainly one of actually being able to resolve or being able to discern very fine details. And the notion there is that there you really actually do need a very large telescope, because the long wavelength array, as the name sort of suggests or hints, it's for the very longest wavelengths. As an example, it would try to observe wavelengths that are, say, 4 to 10 meters in size, so comparable to the room in which I'm sitting, or perhaps comparable to the room in which you're sitting. And that just means one needs a very large telescope to do that, physically very large in extent. And so the original goal of the LWA was to have something that was very large in physical extent, precisely because the long wavelengths mean in order to get the same kind of angular detail, you really do need that kind of physical extent. The square kilometer array was motivated by a slightly different goal, which is the universe is faint. And in order to detect it, in order to detect some of these very distant objects, we really do need lots and lots of metal, effectively lots and lots of little radio telescopes ganged together to form a much bigger telescope so that we can see these very faint objects.
So the basic difference is you're looking at these very large wavelength or objects that are putting out radio signals at these very large wavelengths, or are quiet or faint, hard to see. In terms of the large wavelength array, what kind of objects would be the things that would be giving off those low signals?
For the long wavelength array, there are several. Let me focus on a couple. One, and these clearly reflect some of my personal biases, but one is that, for instance, Jupiter produces radio emission at a frequency, let's say at a frequency of about 30 megahertz, which is a wavelength of about 10 meters. This is, in fact, very simple to detect. You can go, there's a project called Radio Jove, which sells kits for something like $150 or $200. And one can build a small radio telescope in one's backyard to detect the radio emissions from Jupiter. Now, you're probably aware, your audience is probably aware that we now know of other Jupiter-like planets around this, around other stars near the sun. And it probably doesn't take too much thought to say, well, if Jupiter produces radio emission that's detectable, and there are other Jupiter-like planets, orbiting other stars, maybe they also produce radio emission that we could detect here on the Earth. So that's certainly one that's captured my imagination of, can we detect the equivalent of Jupiter-like radio emission from other planets, essentially other extrasolar planets. That's one aspect that's driving the long wavelength array. Another, and much more recently recognized, is that hydrogen, which is the most abundant element, hydrogen, it produces a very specific wavelength of emission at 21 centimeters, And so if I'm holding my fingers up roughly correctly, and if you can see them, it's sort of, it's a little bit less than a foot for those who haven't made the conversion to metric. But 21 centimeters is something like about this size, say. Because of the universal expansion, we do not see, well, let me back up. If there's hydrogen gas, or because hydrogen is the most abundant element, there's hydrogen gas throughout the universe. If you now consider looking at a very distant part of the universe, looking at the hydrogen in that very distant part of the universe, the expansion of the universe means that we don't see the wavelength from that distant part at 21 centimeters anymore, but we see it at, say, 4-meter wavelength or 5-meter wavelength. And those are the kinds of wavelengths that the long wavelength array would be designed to detect. So one of the other much more recent goals, much more recently recognized goals for the long wavelength array is the hope to be able to detect some of these very distant clouds of hydrogen, potentially from which the first stars are forming.
Wow. I was just taking a look at some of the links that you sent. I was wondering if the question of Jupiter and looking at other planets, trying to figure out what kind the signals, if they have similar signals, using those signals to find extrasolar planets. Do we know what actually causes those signals?
Yes, in the case of it's both. This is something that is done. It happens not only at Jupiter but at all of the giant planets and the Earth as well, and that is that the Earth, Jupiter, Saturn, Uranus, and Neptune all have magnetic fields. They're generated deep within the planet by different means for the different planets. But anybody, for instance, who's ever used a compass knows that the Earth has a magnetic field. The sun produces essentially a solar wind of particles, and as that solar wind then hits the magnetic field of the planet, the interaction between that solar wind, that wind of particles that the sun is producing, and the magnetosphere of the planet, or the magnetic field generated by the planet, that interaction is what generates the radio emission. In fact, one of the links I sent you, I believe, was to the magnetosphere of Jupiter. So that's the magnetosphere is the region where the magnetic field of the planet is important. And it's an interaction between the sun's outgoing wind and then the magnetosphere of the planet that produces that radio emission. And so, again, the logic is very simple. And I now see that there is a picture being displayed. The logic is very simple. You have this magnetic field of a planet. If you have a solar wind or this stream of particles that impacts the magnetosphere, there could be an interaction that generates radio emission. That's certainly the case in say Jupiter. Well, again, it's known to be the case in Jupiter, Saturn, Uranus, Neptune, and the Earth. And so it's not that much of a stretch of an imagination, or it's not that big of a leap to hypothesize that, well, maybe this is also happening in some of these extrasolar planets. And you'd put up this picture, just again, for those who perhaps haven't seen the picture, the notion is you have this magnetic field that sort of surrounds the planet. And then as the solar wind streams in, it actually typically forms a teardrop-like shape. And so you can very well imagine that you have this somewhat, in fact, imagine a balloon around an object. And then if you blow on the balloon, it would tend to distort. So there'd be a leading edge where the solar wind is impacting the magnetosphere, but then it sort of gets dragged out behind, and you often get a very teardrop-like shape to these magnetospheres.
Right. So, and depending on the planet and what kind of a magnetic field they have, that shape is going to be slightly different, larger, smaller, and will probably emit differently.
Yes, and not only that, it also depends upon the solar wind or the stellar wind emitted by the star. So if it's a planet that's around a somewhat younger star, we know we have good reason to think that the sun's solar wind was stronger in the past, and therefore the radio emission from Jupiter might have been stronger in the past. All of these kind of details that you just described, the magnetic field of the planet, for instance, how close the planet is to the star, how old the star, all those details come into how much radio emission you would predict it would generate, and potentially how strong it would be here to our Earthbound telescopes.
I was trying to think of from the magnetosphere. There are other things. So extrasolar planets are something that are especially interesting now. People are interested in finding other possible Earth-like planets. Is the large wavelength array, or is it possible to discriminate and be able to, maybe based on the magnetosphere, the signature that's given off, just discriminate on whether a planet is a gas giant or something more rocky like the Earth?
I think potentially most of these searches to date have concentrated on known extrasolar planets, where we already know that, for instance, it was a gas giant. Certainly, however, if you imagine just going and, say, pointing at a random star and saying, is there radio emission associated with that star that we might be able to identify as coming from a planet? There may be a way to distinguish whether it's coming from a gas giant or, say, some kind of more rocky-like planet. My suspicion is that it would probably be a more iterative or more holistic approach, however, in which one would say, aha, we've got radio emission from this object, and it looks like it should be coming from a planet. And if that were to happen, then there would be other people who would train, say, optical telescopes, or you try to figure out other aspects of it, and very quickly then be able to narrow down, okay, it's the combination of all the information that leads us to think this is, say, a rocky planet versus a gas giant.
Got it. Okay, if you'll just stay tuned for just a moment, I need to take a quick break for a word from our sponsor, and so let's say thank you to Netflix. This episode of Dr. Kiki Science Hour is brought to you by Netflix. Netflix delivers movies directly to your home, and that saves you time, money, and hassle. You can instantly watch thousands of TV episodes and movies. You can have them streamed directly to your PC or your Mac or internet-ready device. You can have lots of devices these days: Xbox 360, PS3, Nintendo Wii, Roku, Boxy. You get the idea. All of them are Netflix enabled and able to stream you content, stuff that you might want to watch instantly on a moment's notice. You can watch as many movies as you want, anytime you want, and there are never any late fees or due dates, even if you get DVDs by mail instead of doing their instant streaming. One movie that's available to watch instantly from Netflix, my pick of the week this week, is very consistent with the theme of the show today: Contact. Contact, starring Jodie Foster and a young Matthew McConaughey, directed by Robert Zemeckis, based on the novel by Carl Sagan, and was actually filmed in part at the Arecibo Radio Observatory, which was mentioned earlier in this episode. You can instantly watch this movie or choose from thousands of TV episodes and other movies when you register for a free trial membership. Go to netflix.com/twit. That's Netflix, netflix.com/TWIT. Be sure to sign up for your free trial at netflix.com/twit. We thank Netflix for their support of Dr. Kiki Science Hour and This Week in Tech. So back to the show, we're talking with Dr. Joseph Lazio. He's a radio astronomer, and we're discussing radio astronomy. We were just busy talking about the long wavelength array telescope and the goals for that telescope, enabling it to be able to maybe seek out and find Earth-like or not Earth-like extrasolar planets. Among the other goals of the telescope is to search into the history of the universe, to look back towards, say, the Big Bang. What kind of signals those have got to be just big, kind of dispersed signals from the Big Bang. I mean, we hear about it just being, the thing that we all hear is that the Big Bang, if you could tune your television to a station or your radio to a station that's where it's just static, you're hearing parts of the Big Bang. Is it just a hiss like that?
It is, and there are actually a couple of different kinds of signals of interest. The one to which you're referring is that the Big Bang, in fact, the Big Bang is perhaps best summarized as, in the past, the universe was hotter and denser. Mm-hmm. that's a very both apt and succinct summary. So if you just imagine taking a clock and running it backwards, the universe becomes hotter and denser. And at a particular time in the past, perhaps about 350, 400,000 years after the Big Bang, the universe would have been sufficiently hot and dense that it would have been very much like the surface of a star. That transition from when the universe was hot enough that it was effectively as hot as the surface of a star to the point where it started cooling off so just slightly less than that temperature is an important time called recombination. And what happens at that time, about 350, 400,000 years after the Big Bang, as the universe is expanding and cooling, it's the first time that atoms can actually form. The universe goes from a so-called plasma, or an ionized state, in which atoms can't survive, essentially. You have just, say, protons and electrons, and they're not bound together. But as the universe is expanding and cooling, the important thing is that it's cooling. The result is that these atoms can now form, and specifically most of the atoms that form are hydrogen. That time, at that recombination, is then not only do atoms form, but there is then all of the light that had been present now essentially starts free streaming. The reason the atoms couldn't form is because they were interacting so strongly with the light that was present. Once the atoms form, the universe essentially becomes transparent. So we can look out into the very distant parts of the universe and see the universe as it was, say, 350, 400,000 years after the Big Bang. And what we see in these very distant parts of the universe is this very faint glow, essentially from when the universe made this transition from a completely ionized state in which no atoms can form or could exist to a neutral state in which almost all of the matter was in the form of hydrogen. Mm-hmm. That transition is known as recombination, and one of the things that results is the so-called cosmic microwave background. And that is exactly, if you had an old style TV and tuned it to a station that wasn't broadcasting, some part of that hiss that you were seeing is actually the TV is picking up the radio signals and then translating it into the static or the snow on the screen. That is the so-called cosmic microwave background. That's been an extremely powerful way to probe the Big Bang. Yeah. But what happens next? We now have a universe in which effectively all the matter is in the form of hydrogen, and there are no stars. The stars haven't formed yet. So this is a period of time that we colloquially call the Dark Ages. There are no stars, so you couldn't in fact see any light. There's nothing to generate any light. But of course, the universe wasn't perfectly uniform. There were slight imperfections, if you will, slight areas that were more dense than less dense. And as a result, the hydrogen gas would start falling into these clouds or start forming into clouds from which the first stars would form. And again, as I indicated earlier, hydrogen has this this very unique 21 centimeter radiation. And as a result of these large hydrogen clouds, then the hope for some of these next generation telescopes, such as long wavelength array, and there are 2 or 3 other ones around the planet as well that are going after this goal. The hope is that we could see this 21 centimeter radiation from the very distant universe, from these very first clouds of hydrogen gas from which the first stars would form, or in which the first stars are forming. But again, because the universe has expanded over that time, we don't see it today at 21 centimeter wavelength. We would see it today at, say, 3 meter wavelength or 4 meter wavelength.
Huh. So you have to take into account the expansion of the universe in the measurements that you're taking to be able to get back to what was happening at a particular point in time.
Yes. And in fact, that's one of the very powerful aspects of doing this 21 centimeter kind of measurement, is that we know if you make this measurement of a hydrogen atom, say in a laboratory, it's 21 centimeters. And in fact, the wavelength at which this particular transition within the hydrogen atom is measured is incredibly precise. Because of the universal expansion, it's longer as you go back, or it's a larger wavelength as you consider earlier and earlier epochs. But then you can turn that around and say, aha, if I see this redshifted 21 centimeter radiation, I know when in the universe's history it was generated. So if we can make this measurement, and I want to emphasize it is a challenging measurement, But if we can make this measurement, there's some hope of actually watching the universe evolve by looking at these hydrogen clouds effectively evolving with time, or we would measure effectively different hydrogen clouds at different redshifts or different wavelengths.
Well, that's fascinating. So you could basically take these different measurements at different redshifts and build the history.
Yes. Yes.
Yeah.
Yep.
Basically take that universal evolution, that pathway, like digging down through sediments of the earth. It's fascinating.
That's a very interesting analogy, and I think actually somewhat apt of looking at different wavelengths. Then you can translate that directly in an archaeological sense.
So in terms of doing that, you'd given me a link for reionization from Wikipedia. Does that relate to what you're looking at and how you're measuring this? Would that help to depict what we were just talking about?
Yes, the term reionization, this is one of these cases in which the language hasn't really crystallized yet, or there are a number of different terms that are used for almost the same thing. Mm-hmm. I use the term dark ages. That is sort of the time frame that's relevant before the first stars turn on. As the first stars turn on, people started calling that cosmic dawn. And then as these stars are turning on, then they actually reheat the universe and destroy much of the neutral hydrogen gas, which goes by the name reionization. So the link that I sent you to reionization, I believe one of the figures in there, in fact, is a schematic history of the universe that shows the initial Big Bang and then the formation of the cosmic microwave background at about 300,000 years afterward. There's a long dark period because there are no stars, and then a sort of speckled period, or a period in which the stars are forming, but they're still very dispersed, or they haven't yet really formed into true galaxies. But this is now it appears it was a very rapid process of once the first stars started forming, very quickly thereafter, galaxies were being generated or were forming, and you quickly build up a picture that's not unlike what we see when we look around the more local universe. And yes, the blow up is showing this period of time is probably, say, a few 100 million years to as much as a billion years after the Big Bang. And again, going back to your archaeological analogy, if we can make these kind of measurements, you could potentially track, for instance, how the stars are forming, how rapidly they're forming, how massive they are, how big they were, and actually watch this process of going from essentially no stars in the universe to these galaxies, these mature galaxies evolving or forming.
Now, the data that you've been working with so far has been from the large wavelength demonstrator array. And it's not as big, or it's not as fully developed as what the large wavelength array will be. How is the data that you've got so far, kind of this pilot data, telling you that you're on the right track?
Right track.
That you're going to be able to, that you're going to be able to get what you hope to.
It's a very good question, excellent question, and that was in fact one of the motivations for building the so-called long wavelength demonstrator array, or the LWDA. It was precisely that you construct a small prototype of the system and make sure that it works at some level before you embark on building a much larger array or much larger facility. The LWDA had 16 dipoles in it. The dipole, in fact, one of the things even before the LWDA was constructed, and this was work that was led by the United States Naval Research Lab, even before the LWDA was constructed, there were individual antennas constructed, again, along the idea of, are we even on the correct track here? And after you do tests on one antenna, then you say, okay, we think we understand how this one antenna is working, and many of the lessons that you learn from that, then you build out some more numbers, say 16, which was the case for the LWDA. The antennas for the LWDA, in fact, I don't remember if I sent you a picture, but I certainly sent you a picture of the LWA. And the LWA antennas owe considerable heritage to the LWDA antennas. They look like sort of broken ceiling fans, if you will, or droopy ceiling fans. Again, and that's much because the LWDA was constructed precisely as a test bed. And then along the way, it was a case of, oh, you know, we can get some science out of this as well, or we could try to do some scientific experiments. It's not just an engineering or a construction prototype. We can actually do a little bit of science. And as you said, or as you asked, quite rightly, are we on the right track?
The question is, are you on the right track?
and again, everything that we've seen to date, and certainly the LWA, the first station of the LWA is now turning on. From what I've heard, I missed the most recent conference because of some other details or some other commitments, but it certainly looks like the data are looking very good, and all of the lessons that we learned from the earlier work have been paying off, and things are looking good. Obviously, this is still in the very early stages of the operation of the LWA, but we have every reason, or we don't have any reason to doubt that we're on the right track.
What's your time frame for the LWA, and what kind of data, like what kind of results should we be expecting, in what kind of a time frame?
Another good question. The LWA itself, all of the hardware components were recently finally all connected, or all got to place and connected. And indeed, there's a picture now being shown of this field of LWA antennas, again, looking very much like perhaps a broken or a droopy ceiling fan. What you're seeing is actually just part of the LWA. You're seeing the actual receiving elements. So the radio waves come in, they strike these metal antennas and are then converted into electrical impulses. What this picture does not show then is there's an additional hut of a number of electrical and computational equipment. And that's the part that all of those components have just finished being delivered and are being finally tested, and end-to-end tests are being developed. So on the timescale of sort of, well, now or within, over the next month, all of those kind of tests are being worked out. Over the course of, say, the next 6 months to a year is the timescale on which people are thinking about really taking serious data that you would use to start testing some of these ideas. Mm-hmm. And again, some of these measurements are quite challenging. So, for instance, probing into the dark ages, it might very well take us a year to 18 months to fully debug the system and get to the stage at which we have an adequate amount of data. Because, again, these are very faint signals, so we need to observe the sky for a fairly long period of time, or a fairly long interval of time. Yeah. It might really take us 12 to 18 months before we have enough data and have really debugged the system to the extent that we could believe a result.
When you say that you have to look at the sky for a fairly long period of time, is it kind of like taking a long exposure picture with a camera, like of the night sky? So you have to look for a longer period of time to get a clearer picture?
That's you just nailed it perfectly. That's exactly what is the issue. The sky is very faint, either at optical or radio wavelengths, and it just takes a little while. It takes sometimes a long while to get a long enough exposure that you can see the kind of faint objects that you're hoping to see.
Yeah, is part of the debugging that you're talking about, does that have to do with filtering out noise? Someone in the chat room is asking this question.
Yes, and in fact, I haven't really converted some of the wavelengths to frequencies. Let me do that now. For instance, I've said 4 meter and 3 meter wavelengths. Well, 4 meter wavelengths or a wavelength of 4 meter converts to about 75 megahertz frequency. And at a 3 meter wavelength, which actually the LWA does not operate at 3 meter wavelength, there's a very good reason why it doesn't. 3 meter wavelength converts to 100 megahertz, which is smack in the middle of the FM radio band. So in fact, a ground-based radio telescope has considerable difficulty operating amidst the radio pollution, essentially, that is generated by our own activities, such as FM radio and TV, and at higher frequencies or at shorter wavelengths, say cell phones and things like that. In fact, one of the pictures I sent you, or I sent you a movie, and this might be an excellent time to display or to play that movie, because it does illustrate a couple of things. Those who can see it, what is actually being shown, these are data from the long wavelength demonstrator array, or it's a movie that was put together at the LWDA. It shows the sky at a frequency of 60 megahertz or 61 megahertz, which is about 5-meter wavelength. And it immediately demonstrates two things. One, it demonstrates why we want to look at these different wavelengths. If you can see the movie, what you're seeing, the most prominent things are if you ignore some of the occasional flashes that occur, the most prominent things are 3 bright blobs. Those bright blobs are the 3 strongest radio sources in the sky. None of them are visible to the human eye. One is the remnant of an exploded star. One is the core of a distant galaxy, and one is actually the center of our own Milky Way galaxy. And again, none of these actually show up all that well at optical wavelengths. Actually, the one galaxy does, but for instance, this remnant of the exploded star really doesn't. Then as you're watching this movie, you are seeing these occasional little flashes. These little flashes are actually reflections of distant TV signals. What is happening every time you see one of these little flashes? What is happening? This movie actually was made in November of, I think, 2006. And any amateur astronomers in the audience probably know that November is the time of the Leonid meteor shower. As meteors come in to the Earth's atmosphere, not only do they burn up and create what we would call a shooting star or meteor, they leave behind them a little trail of essentially ionized material for a short while. And a distant, say, TV station or a distant radio station, the signals from that can reflect off this ionized trail in the Earth's atmosphere and be reflected into effectively into our telescope viewing. So all those little flashes are effectively reflections high in the Earth's atmosphere off these ionized meteor trails. It's an illustration of the kind of signals that when you say debugging or trying to figure out the system, one of the things is certainly where are what we would call radio frequency interference signals being generated? Can we filter those out in some way, either by, for instance, not observing at certain times or not observing at certain frequencies? And then you also mentioned I'm involved in some lunar radio astronomy activities, and this kind of movie is an excellent illustration of why we'd like to go. Ultimately, I think it will take some time, but why we'd ultimately like to put a telescope on the far side of the moon, because it shouldn't have any atmosphere to generate these ionized meteor trails, and it shouldn't have any humans with FM radio or TV stations that would be corrupting our signals.
Right, and being on the far side of the moon would be blocking the telescope from those signals emanating from the Earth, right?
Exactly right. Several thousand kilometers of rock is a very good shield.
It's fabulous. If you can get a shield that big, use it.
Yep.
And we have one just floating out there.
Yep. All we need to do is go there.
You mentioned amateur astronomers, and there were some people in the chat room wondering, is it easy or helpful is amateur astronomy an easy way to get into radio telemetry or radio telescopy? To be able to actually get into collecting data, because we see amateur astronomers making visual optical discoveries, but are they making radio discoveries as well?
Not perhaps to the same degree as in the optical wavelengths, because in the optical wavelengths, it is certainly much easier to, for instance, or I suppose the way to say it is a much smaller telescope can give you a significant bang for the buck, whereas in radio, at radio wavelengths, the universe is pretty faint, and you really do typically need large telescopes. That's not entirely, or it's not always the case. I think the two significant exceptions, one would be, I already mentioned this Radio Jove project, and Radio Jove is an example in which a fairly simple outfit, again, it's $150 or $200, one can put together a radio telescope and specifically the electrical components to it. So it's a very good exercise, say, for high school students. In fact, I was involved at one point in a high school that was putting together this a radio telescope, or that some of the students were using this kind of Radio Jove or this kind of kit to essentially learn how to do electrical and technical work. And from the standpoint of really doing an end-to-end system, there are ways, and in a more electrical or computational perhaps than you might think of for optical telescopes. That's certainly possible. I also know that there is a group of amateur radio astronomers who are interested in doing things like searching the night sky, essentially for anything that goes bump. And one of their main motivations is possibly searching for possible signals from other civilizations. And that's a case in which it might be better to have lots of small radio telescopes scanning the skies continuously than one very big radio telescope on which it's difficult to get time because everybody else wants to use it as well. So those are certainly the two cases of which I'm aware in which amateurs can really make interesting measurements today, and often with not that much investment in terms of hardware and cost.
Right. Could you potentially use discarded satellite dishes? As
Yes.
part of the array?
Certainly, from the standpoint, that was certainly one of the things that's been motivating the square kilometer array for some time, is to take advantage of exactly those kind of advancements, that a combination of perhaps being able to essentially stamp out dishes the way that satellite companies do, take advantage of some of the developments in signal processing, say from cell phone or gaming activities or gamers. All of those kinds of things actually push on technology, sometimes in very interesting ways for radio astronomers or astronomers in general.
I think it's just great. We're getting to the end of the hour. You mentioned that you're interested in getting a radio telescope on the far side of the moon. Is that something that you're actively doing and that you're hoping to be pushing for in the near future?
Certainly, I am involved in a group that is looking at that. I think an actual telescope on the far side of the moon is going to be a long time in coming. We do have a concept for putting a single antenna on a lunar orbiter that would go around the moon. That is something that potentially one could do in the next decade. Or technologically, that is feasible within the next decade. And that is perhaps, as you say, we're coming to the end of the hour, conversation for another time. But it is possible to get into that shielded zone behind the moon and make potentially very interesting measurements about the dark ages of the universe on a single antenna on a lunar orbiter.
Excellent. I think that about does it. What are you working on? I mean, the large wavelength array, the square kilometer array, the spacecraft. You're keeping yourself busy. Is there anything else you're working on that we should be aware of to be paying attention to in the near future?
I think that I do have my fingers in a number of different projects. I think you've gotten a good summary. One of the things I've not been able to do is figure out how to get more than 24 hours in a day. But if
to
one
Mars.
of your yes, if one of your other interviewees could suggest something like that, I'd be most interested in that.
Excellent. Well, thank you very much, Dr. Lazio, for joining us today on the Science Hour. It's been really, really interesting and very educational. I think I've learned a lot, as well as people in the audience.
My pleasure. Glad to have done it.
Yeah, and if anyone out there is interested in learning more about radio telescopes, specifically the long wavelength array, you can go to lwa.unm.edu for more information, or you can go to SCA Telescope for the Square Kilometer Array Telescope. scatelescope.org is the website if you're interested in more information on that. And as we can see, there's a whole wealth of information out there in Wikipedia if you're interested in delving into this information a little bit more deeply. I'm Dr. Kiki, and this has been the Dr. Kiki Science Hour. Next week, we're going to be talking about something really interesting, maybe something to do with talking cars, maybe? Yeah, maybe we'll be doing that. Anyway, until then, you can follow my sciencey pursuits. Just go to Google, look for Dr. Kiki. I'm on Twitter as Dr. Kiki, Facebook as Dr. Kiki, and right here at Twit as Dr. Kiki. You can subscribe to Dr. Kiki Science Hour in iTunes. You can find past episodes here at the Twit Network, twit.tv/Kiki Kiki. And if you need even more sciencey goodness, be sure to tune in to This Week in Science, which you can catch at 7:30 p.m. on Thursday evenings Pacific time here on the TWIT network, or you can go to the website, which is twist.org. So much science, so many websites. We need more time, really. We do need more hours in the day. I'll see you next week. I hope to be healthier by then. And thanks for tuning in to my Science Hour. All I do ask is 1 hour a week because, that 1 hour a week is sure to make your world a whole lot more interesting.